all set. All right, last time we were talking about recursion, and we saw how anything we can do with recursion, we can do with like iteration, with loops. And anything we do with loops, we can do with recursion. But just because we can doesn't mean we should. And sometimes the algorithms, like we saw like with the Fibonacci numbers, that it was such a simple algorithm. It was so simple. The code was like 4 lines of code. It was glorious. But we saw in practice the computational complexity of that algorithm was horrible. It was like 2 to the n. Where n is like, yeah, it was hilariously bad. Where the iterative version, not really an overly complex algorithm, but a little bit more sophisticated. But it's linear time, which is way better. Now, it's funny because with recursion, that's not true. I would say now that we're playing with recursion and some of these problems, we can become a little bit more aware of some of the types of algorithms that are just bad in terms of how long they would take to run. And like with Fibonacci numbers, both of the algorithms we saw, the recursive implementation, which by the way, you can make a recursive implementation that is linear time. You can do that. But the standard typical recursive function is an algorithm that will solve a problem, the Fibonacci numbers. And the iterative version of the algorithm is an algorithm that will solve that problem. But we have 2 different algorithms solving the exact same problem, but one is linear time, which is awesome. Then the other one is just absolute trash in terms of computational complexity. So it's interesting how, like, yeah, these 2 different algorithms, one is a good choice, one's a bad choice. All right, so now we'll talk a little bit about the story of the Towers of Hanoi. And this is, of course, a nonsense story, but you got to go with me. And I guess because I'm sharing my screen, so I have to leave it like this so I can read it. But Towers of Hanoi, okay? So basically, have you ever seen this puzzle before? I know you have, right? And the goal is, okay, you got to get all the discs from this peg to one of the other 2 pegs. And you can only move 1 disc at a time. And at no point can you have a smaller disc below a bigger disc, right? So I know you've all seen this problem before, this little toy. And there is such a simple recursive algorithm to solve this. It is hilarious how small it is. And here it is. All right. Oh, wait, no, that's what we want to do. Okay, and here's the demonstration of how it works. So here is the Towers of Hanoi recursive solution. We're not going to look at it in code, but here it is. Move n disks from the original peg to the destination peg. Wait, do I have a nicer recursion algorithm iterative? Okay. So if I have n disks I need to move, here's what we're going to do. I need to move all n disks from here to there. I'm going to move the top n-1 disks from here to the middle peg, then take the biggest disk, put it on the final peg, and then take all of the n-1s from here and put them on that peg, the destination one, so on top of the bigger disk. And there we go. That's it. That's it. That's the algorithm. It's simple. Now, I'm willing to bet everyone here is going, well, hold on a second. You just said move all the n-1 disks. And that could be a lot of disks because you can only move 1 disk at a time. That's the rule. And you're absolutely right. But you want to know how we're going to move those n-1 disks? With a recursive call to this function, where we'll end up calling n-2 disks, and then n-3 disks, and n-4 disks. But if we go back here, here's the story. It was a puzzle invented in the 1880s by some dude named Edward Lucas. And it's based on a legend involving monks moving 64 golden plates from one place to another. And it is said that the world will end when the monks finish their task, okay? So here we go. The legend. Long, long ago, in a place very far away, there was a temple containing 64 sacred golden discs. The monks needed to move the discs from one location to another, okay? So maybe there were some discs over here. They needed to go over there. The discs are very fragile and they are priceless. These discs are so important to our universe that we have to be really careful with. So we can only move one disk at a time. A disk may not be placed on top of a smaller disk, a smaller or less valuable disk. That is against the laws of our universe. The gods will be very angry. And there's only one other location in the temple. Besides the starting place and where we need to move the disks, there is a sacred table that we're allowed to put the disks on. So we can put disks on that table there, but ultimately the goal is to go from here to there, and they can only exist here, there, or in my hands. So the monks start moving the disks back and forth between the original pile and the pile in the new location, okay? And the intermediate location, of course, which is always keeping the pile, and we are making sure to always keep the piles in order. We can never have a smaller disk below a bigger disk. I mean, we can have a really, really, really big disk and a very small disk like this, but nothing like this ever. That's bad. So it was said that when these monks complete their tasks, the universe will end. Okay? Now, isn't that a fascinating story, right? So, wait, I don't know why I didn't just change the screen, but whatever. Here's the funny thing. If I'm moving 64 disks and I'm following this recursive algorithm here, which if I told the monks, execute this algorithm, if I went to the monks and said, okay, here's what you're going to do. You're going to move all those disks that are on top of that biggest one on the bottom to that that sacred temple. Then move the big one, put it over there, and then take all the disks from the sacred pedestal temple thing and put them over there. And then, like, well, how do you move those ones? Well, okay, then you need to move all the ones on top of it to there, and then whatnot and whatnot and whatnot. If you follow this algorithm, it ends up being a 2 to the n scenario. So if I have to move, where n is the number of disks in this case. So if I had to move 64 disks, what is 2 to the power of 64? Oh, no. There we go, 64. What do we got here? Holy moly. Okay, so it would take that long. So if we take that number, let's say, what do I say down here? I say, let's assume a monk, let's assume that these monks are so well trained at transporting these disks that they are so good at it that they can transport a disk to where it needs to be on average once a second. Okay? So if it would take them once a second, so that's how many seconds it would take. Okay. And let's take that and divide that by 60 to know how many minutes it would take. All right, well, that's a really big number. So there are 60 seconds in a minute, and then there's 60 seconds in an hour. So let's do divided by 60 again to figure out how many hours it would take. Okay, and then there's a 24 hours in the day, so how many days would it take? Okay, and then there's 365 days in a year. So let's see if we do divide by 365. Wow. What do we got here? What is this number? 584, almost 585 billion years. Wait, is that right? Billion or, wait, 1, 2, 3, 1, 2, 3. That's million, that's billion. Okay. So it would take 583 billion years if these monks can move these disks once a second. And that's fast. But it looks like we're okay. It looks like the universe isn't going to end anytime soon. We got a couple of billion years to go before the monks finish their job. But interesting nonetheless. Point being, this algorithm here, that sure, it's like pseudocode E, but I can explain this algorithm to a human and a human can execute it, or I can tell it to a computer and a computer's really fast, right? So let's say the computer can do it in, instead of once a second, let's make it once every, if they could do that once, so there's 60 seconds, so there'd be milliseconds. I mean, let's make it like, well, even if I made it like an order of magnitude, even if I made like it, like, well, they can move 1,000,000 disks a second, that would take 584 years still, right? Divide by 1,000,000, 1,000,000,000,000. Wait, no, more than that. Oh, man. It would take 538,000 years, right? Yeah, because even if I said that we can do 1,000,000,000 a second, let's say we can make our computer move 1,000,000,000 disks a second, it would still take 580 whatever years. That's crazy. The point of this exercise, this thought experiment, this little story, is to demonstrate that sometimes, although this algorithm, we're not going to go in more detail about this particular algorithm because it can get a little hairy. But the point is, this seemingly beautifully simple algorithm, which I could tell you is guaranteed to work, would take so long that it would take longer than the universe has existed if humans were doing it. You know? Like, it's crazy to think that, yeah, there are some problems out there. If you have like a bad algorithm for it, it's just not computationally tractable. It's not reasonable to expect to actually get an answer to some of these questions. It would just take too long. So, okay. So, a little bit on algorithm analysis. So, when we were doing iterative analysis, when we looked at loops and whatnot, it was kind of straightforward, right? Like the trick kind of is, and you really shouldn't be doing this as a trick, but I always do this as a trick, is you look for the loops to get a sense of how many times the operations and lines of code are going to be run. And we kind of think about it in terms of the size n, right? Input size n. So for example, if we looked here, if I was summing 0 to 5, well, I mean, this is going to run to 5, but let's say I wanted to count the sum up to some arbitrary value n. Well, it's going to be n, right? Because like, well, how many times is this loop going to run? Well, it's going to run n times. So, and if I double the size of n, it's going to have to run twice as long. So the trick a lot of times that I do when doing the iterative stuff is I just look for the loops and see what's going on. But the recursive stuff gets a little bit different. Actually, no, it doesn't get different. It's just that the trick of looking at the loop kind of goes away. So the problem still remains. How many times are these operations going to be run in terms of the input size n? And here's what we got to do. All we have to do is, well, how much is done in a single run of the function, and then how many times is that function going to get called? Because if I know how long it takes to run the function, and I know how many times it's going to get called, well, you just like multiply it together. If the function is like order 1 and the function's going to get called n times, well, it's order n. So it's still the same idea. How many times is this code going to be running? Where the loop is obvious because that's what a loop does. And recursion, I guess, is obvious too because we know that recursion just keeps calling the same function over and over and over again. So what's the order of this function? Well, this is order n. Now here, recursive sum. What's the computational complexity of this? Well, let's think about it. Oh, and I'm still missing my little pen. So I guess I'll have to do this with my mouse. Hopefully it's not horrible. No, that's a laser pointer. Pen. So what's the computational complexity of all this? Well, I mean, we know this is a recursive function, but like checking this, easy, return 1. I mean, this is all order 1. Adding n to some value here, this is order 1. So one call of this is, can you hear that vacuum on? Hopefully it's not too annoying. But then the question goes, well, how many times is this function going to run? Well, it might be obvious to you, but if it's not, well, let's think about it. I put in an n here, some arbitrary value. So I start at n. And the next time I call it, it's going to go to n minus 1. And then the next time I call it, it's going to be n minus 1 minus 1, because the n will be n minus 1. So it'll be n minus 2. Dot, 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 dot. But when does it end? It ends when n is 1. So it'll go all the way down to 1. And if we go from 1 to n, what do we think that is? How many times is this function going to get called? Well, n times. I heard a boop. N. Exactly. You're 100% correct. Damn, those some old monks. All right, I missed that. So if we're doing an order of 1 operation n times, it's going to be order n. And again, remember, it's about how it scales. If I doubled n, it's just going to run twice as long. What's the order of the function? Yeah. How many times will the function be called? There we go. Now, how about this one? Well, we actually already kind of did this one, but think about it. How many times? So 1 run of this is order 1. But how many times is this function going to get called? Well, for every 1 function call, we're going to call 2. And we're going to call 2 until we go down from n to 0, basically. And I realize this one's counting down at a faster rate, but let's be lazy and just think of the n minus 1. So we're going n to n minus 1 to n minus 2 ... to 1, right? And we have 1 function call, and then we have 2 function calls, and then each of these has 2 function calls, and then each of those has 2 function calls. Right, so let's kind of draw it like that. Boop, 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 and so on and so on and so on. So the question is, well, how many are going to be down here? Well, I mean, we know that's going to be 2 to the power of n-ish. I heard boops. Couldn't we just give it the current fib number and the last one and make it order n, like in the iterative, but make it recursive and stop at the right index? Couldn't we give the current fib number and yeah, of course we could. Yeah, like I was saying, anything we like, I could make a linear time recursive version of Fibonacci. But if we look at the pure Fibonacci like mathematical definition, it is a recursive definition. But if you were to go computing it, it would suck if you're following that algorithm. Yeah, oh yeah, there we go. Yeah, all right, it's 2 to the n. Very bad, but the recursive solution is so nice and simple. Yeah, but iterative one is very ugly and gross. It is. Real life, recursion pops up everywhere. Okay, cool. Great. Any questions about that before we go on to learn about an awesome data structure? How are we doing with that? Everyone okay with that? Or any questions about what we just saw? So typically on the final exam, I would have like a chunk of the assignment would be about like computational analysis, computational complexity analysis. But the trouble this year is because it's going to be a take home, I'm not really seeing that as being practical. So I'll warn you that this is a very important concept, especially like when we get back in person and whatnot, you're going to need to know this stuff. But it won't be like, I won't really be able to test it particularly well this year. There might be some questions kind of on it, like make sure you write an algorithm that is this computational complexity for this particular problem. That might be there, but don't think that this stuff isn't important. This is critically important. So yeah, any questions before we move on to the trees data structure? Keep an eye on the time. Oh yeah, we're good. Oh yeah, we're good. Okay, seeing none, let's carry on. So, a tree. All right, the point of this lecture, what are trees? Tree terminology. Okay, I'm going to warn you. There's going to be a lot of definitions and jargon introduced to you right now. But fortunately, they're very natural words that one would use to mean these things. But I'm going to warn you, it's time for memorizing some definitions. So a tree is a non-linear data structure. And that's a fancy way of saying, like, you know how like in a list, if I asked you what comes next, you know, right? But if you had something like a file system and I said, what comes after C:// your answer is, well, I don't know. It depends on where you want to go because there's not like one line you would follow. And the data does tend to be hierarchical like family trees. Child and then the parents and then their parents, or inheritance like in computer science. File systems on a computer, like I just said, decision trees, table of contents in a book. Yeah, and that really is kind of like a tree if you think about it. The information on this slide is structured in a tree format. This would be like, the slide would be like the root, and then here we'd have things, and this would be a sub, and this would be a child node, and whatnot. But anyways, here's a very simple idea, right? Here's a computer's file system. We've got our root or C drive, our documents and settings folder, our program files. Maybe we've got a folder called My Music right under there, and so on and so on and so on. See, there's a tree. So a tree is a collection of elements of the same type such that it is either empty or it has a distinguished element called the root, which descends 0 or more trees that we would call subtrees. This is a recursive definition. The tree is either empty or has a root and has subtrees. And the subtrees might be empty because we know that the subtrees are trees, and if it's empty, it's a tree. But that's the definition of our tree. So in this case, this is the root. This is a subtree. This is a subtree. This whole thing's a subtree. And then this part right here is a subtree of this one. And I mean, this is a subtree of that one. And I guess, I mean, down here, there are some subtrees that are just basically empty, but they're still subtrees. Yeah, so there's the root. These are called interior nodes, and these are called leaf nodes. So you might think, wait a minute, why is this tree upside down? It is. So the root's at the top, and then the leaves are at the bottom for some funny reason. And stop. Doesn't the root have no root and is not empty? Doesn't the root have no root and is not empty? I don't understand your question.
Like you said, it either has a root or is empty, but the root doesn't have a root because it doesn't go to anything and it's not empty?
But the root is the root. It has no, a root is defined as one thing that has like no parents.
Oh, so it's its own root. God,
So the root
no.
is like this tree's, but this right here is the root of this subtree. If we pretend, okay, well, let's ignore this one here. Well, now here's the root of this subtree. And then this is the root of this subtree, but I mean, this is empty and whatnot. Think of it also as like, if we think of a string, remember like an empty string is still a string, where no string at all is no string. Like if I created a variable called string and went like open quotes, close quotes, and there's nothing here, it's a string, but of length 0, you know? So remember that, that's important. So some tree terminology. Okay, wait, no, hold on, yeah. Root, leaves, and everything in between, interior nodes. Tree terminology, we've got nodes. These are the elements in the tree. We've got edges. These are the connections between the nodes. And we've got a root. This is the special, super special element that is the origin of the tree. And the trees only have one or no root nodes, because technically if it's an empty tree, there is no root. Leaf nodes, they're the nodes that have no child nodes. More on what a child node is in a moment. Interior nodes, those are the nodes in between. They're not a leaf node or a root node. Empty tree, a tree that has no nodes or edges at all. But by definition that we're using, it is still a tree. Just think an empty list. You've got a list, but there's nothing in it. It's still a list, though. Now, a parent or a predecessor, that's the node above in the hierarchy. And if you're a root, there is none. And each node can only ever have one parent or none. Yeah, if it's the root. Right? Yep. And then the child, well, that's like the opposite. The node's directly below, and each node can have between 0 and many child nodes. So if I have like some root here, I don't know why this happens. I could have like 1 billion child nodes. Or I could have, here, perfect, there. Or none, right? Because the child nodes we know have none. Siblings, well, they're the nodes that have the same parent. Honestly, we don't really use this a lot. Ancestor, one of the parents or the parents' parents or the parents' parents' parents. Basically, if you can track its lineage, that's an ancestor. A descendant, that's the opposite. So here we go. So, I mean, this right here, the root will obviously be the ancestor of all nodes in the tree, right? But this node here, this one over here is not one of its ancestors. All right, so can a leaf node, here's a quiz. Can a leaf node have any children? It's a tough one. Type in the chat. None. Good. Does a root have a parent? No. Good. Excluding the root, how many parents does each node have? Oh. 1. Good. All right. A path. Now, this is a sequence of nodes and edges leading from one node to another. So we can have a path from here to here, And that path would be this. Right? So we can go through the root. So we're going like up and then down. And that is a valid path. And the length of path is the number of edges. Everybody, say this out loud wherever you are. The number of edges. Not the number of nodes, the number of edges in the path. So in here, the distance from here to here is 1, 2, 3, 4, 5. This is 5. If you go, well, it's 1, 2, 3, 4, 5, 6. No. Count the edges. Count the edges. If you insist on counting the nodes, just don't count the first one and you'll be fine. So number of nodes minus 1. You took the words kind of right out of my mouth and then put it in chat. Good. Path, a sequence, yeah. Length of path. Height of a tree. This is the longest path from the newt to any leaf node. So here, what's the longest path? Well, we got 1, 2, 3, 1, 2, 3. It looks like the longest is 3. We can have 1, 2, 3. Yeah, it looks like the height of this tree is 3, not 4. So what's interesting, imagine I had a tree that was, imagine this is my tree. And there's no children. R for root. What's the height of this tree? I mean, like, remember that, like, these edges, they're not really there because it has no children. So what's the height of this tree where it's only a node, where it's only the root? Bingo, it's 0. Now, what is the length of this path? What is the height of the tree with only a root? Oh, spoiler. What is the height of a tree? Oh, I think that the length of this path was supposed to come up earlier, but whatever. What is the height of an empty tree? So imagine I had a tree that was like nothing. It was just empty. No. So I'll draw the, what do I draw? What is the height of a tree with nothing in it? Now this is kind of sticky because it can come by, well, by definition, it will be. But -1 is the correct answer. That's what we are going to use, is the height of a tree that's empty is -1. Level of node is the number of edges between the root and the node. Nope. So level 0, level 1, level 2, level 3. So 1 edge, 2 edges, 1, 2, 3 edges. Level 0, it will be the root. Recursively, the level of root is 0. Level of a node that is not the root is level of its parent plus 1. We can do that recursively, great. Tree discussion, okay. What is the level of a node in relation to the path length from the root? Oh. This is, it's not a trick question, it's that simple of a question. Bingo. What is the height of a tree in terms of its levels? Ooh. Come on, this is a tough one. And by tough, I mean easy, but come on. Someone's got to know. Don't fall asleep on me. It's still morning. It's not even lunchtime. There you go. You're right. So a subtree, a child node, and all of its descendants. A subtree itself is a tree. A node may have many subtrees. So this is a subtree. This is a subtree of the root. This is another subtree. This is another subtree. Technically, this is the subtree of that one. This is a subtree of that one. This is a subtree. This is a subtree. This is, and so on and so on and so on. Yeah. What is, okay, what is the root of the subtree labeled E? What? What is the root of the subtree labeled E? It is E. I guess that's what I'm trying to ask here. It's E. The root of this subtree is E because it's at the top. Degree or arity of a node. Usually I only ever use the word degree, but I have seen arity. It's the number of children a node has, it doesn't count the parents. And the degree or arity of a tree is the maximum degree of any of the nodes. So here, if I look at this one, what's its degree? Well, it's 2. What's this one's degree? Well, it's 0. This one's 2. This one is 1 because there's 1. This one is 3. And if I keep going, we'll end up seeing, well, this one has 4. And this one only has 2, and then this one has 1. These have none. So, I mean, that's what each one's degree is, but then I would take the maximum of all this. So I've got 4, 3, 0, 2, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 2. It's 4. So what's the degree of this tree? It's 4. Yep. Awesome. Isn't that awesome? We just learned about trees. Now, can anyone think of the relationship between trees and lists now? Anything? Can you think of anything interesting? Sheesh. I don't want to go back because as soon as I do, it's going to open up PowerPoint in the wrong virtual desktop. It's a whole thing. All right. What's the difference between those 2 degrees? What?
Like on that slide you just did, there was 2 bolded degree/arity things.
Oh, one was... Okay, let's go back and have a look. Now that I've closed it, let's go have a look. Ooh. Hopefully it'll open faster because PowerPoint's already open. My goodness, my poor computer. Oh, these 2? So the one's for a node and one's for the whole tree. So any given node, if I ask you, okay, what's the, if I ask you like, what's the degree of this node? It's 2 because you count the number of children. But if I ask, well, what's the degree of this whole tree? It's the maximum of the degrees of all the nodes in the tree, which in this case, it's 1, 2, 3, 4. It's the root that has 4 children. Was that your question?
Will it always be the root, or if you had like another?
No, it's like
Okay.
here, I can do this. One, 2, 3, 4, 5. There. Now it's this node. It has 5 children because I just added them. So yeah, it's not always going to be the root. It's just a coincidence. Was that it though? That's your question? Just making sure.
Yeah.
Awesome. Cool. So yeah, any questions about that before we move on? And I do want to ask about can anyone think of the relationship between a list and a tree? Like, what's there? Is there anything there that you think's kind of interesting? And look, I know you don't know. I've never taught you this, but let's just kind of like brainstorm and think for a second. Like, a tree would be a list of lists? I kind of see what you're saying. You know what? A bunch of lists that link up? Yeah, totally. I see what you're saying, but you know what? What if we go the other way? So a tree looks like it's a list of lists, and it totally seems that way, doesn't it? But what if we go the other way? What if we say, could I make a tree by the definitions that we just learned? A list is a path in a tree. Yeah, you're totally right. That's correct as well. Can I make a tree based on everything we learned about a tree? Can I make a tree that is by definition a tree, but that is totally a linear list? How? Because the answer is yes. Using node list. You might, yeah, okay. I think Johannes I think you meant what Jared is saying, but yeah, just, you have the root, that's the head. And then each node only has 1 child. A list is a tree of degree 1, right? So a tree is actually a generalization of a list. Like a list is a tree. I mean, a tree, we can do more with a tree. All lists are trees, but not all trees are lists, right? So it's kind of neat. Anyways, we'll now start talking about, looking at the time, will we start talking about? All right, tomorrow we'll start talking, we can do more with a tree, environmental science majors probably. You can do more with a tree, I'm just saying. Tomorrow we'll start learning about a specific type of tree, a binary tree, which is a tree that has a degree 2. So at most, any node will have 2 children. And then after that, we're gonna learn about binary search trees, which are even a more special version of a binary tree. We won't start that now because there's no sense starting the next couple of minutes. But I suppose before we wrap up, I mean, we've got like 6 minutes left. Are there any questions about anything up until this point? And no, I have not made your exam yet, if that's what you were going to ask. I have to figure that one out still. It's on my to-do list, though. You know, I'll stop recording for the time being.